I see 101 students. So the topic remaining from week 14, day 1 for exam 3 is the LeChatelier's principle. This is the last slide I went over, right? I talked about you can apply these different types of stress to a system at equilibrium, right? To make the equilibrium shift in the direction to relieve the applied stress. Right, so let's look at each of these individual stresses. All right, so the first stress we're going to talk about is addition of a reaction component. For example, if we look at this reaction right here, right, A plus B going to C plus D. Right, so you have a reaction, we have A plus B going to C plus D. Right, so in this PowerPoint slide, A is going to be added. Right, that's why this is in red. So let me do that as well. All right, so now what I'm going to do is, we're going to add more of A. Oh, should that be? Now what happens, right, is, so again, this was at equilibrium, you added more reactant A. That's why this is in red, right? Now, when you do that, what's going to happen is, when you add more of reactant, what we say is, we say the result will have the equilibrium shift to form more products. Or this is the same as saying the equilibrium shifts to the right. All right. Then again, what happens is, after the equilibrium shifts to the right to form more products, right? So you're going to form more products. The system will re-establish equilibrium. Now keep in mind, right, the equilibrium constant K value does not change for this particular reaction, even though you added extra A, right, to the reaction at equilibrium. All right. All right, so now instead of adding A, what we can do, right, is what happens if we add D to the same reaction. Right? So for example, now what we're going to do is, we're going to look at a scenario, same reaction, A plus B going to C plus D, A plus B is at equilibrium C plus D. All right, now remember, C plus D are my products. Now what I'm going to do is, I'm going to add more of D to the reaction vessel. All right, so when that happens, right, when you add more D, same thing, all right, the equilibrium will shift toward the reactants. Right, you add more of D means you're going to form more of A and B. Or in other words, the equilibrium shifts towards the reactant to relieve the stress of adding a product. All right, so to maximize the amount of A or B, not remove, that's incorrect here, so please fix it, right? We can add D to the system. All right, go ahead and save this. All right, so now instead of adding, what I've not talked about is removing a product. All right, so now we're going to look at a real life application. All right, for example, this is the reaction. So think about acid rain, right? When acid rain falls on statues like these, all right, so this is made up of marble, right? This marble is calcium carbonate. So H2SO4 is my aqueous rain. All right, you form this product, right? So what happens is, marble starts etching, right? And that's why you see all these holes, if you want to call it, right? Or the degradation of this marble, right? What we can think about this is this reaction is at equilibrium, right? So think about this as again A plus B going to C plus D. In our reaction, we have C plus D plus E. The reason I do that is in this PowerPoint slide, we have three products, one, two, three, right? Carbon dioxide is one of my products. So let's say that C or D is my carbon dioxide, right? Now, what happens if you look at this reaction, all of these are aqueous. This is aqueous, meaning think about this as being dissolved in water, right? This is solid, this is liquid, but this is gas right here, carbon dioxide gas. What I'm going to do is I'm going to remove carbon dioxide. So, right, when I remove D, so we're looking at remove D. So if you remove D from this reaction, all right, more products will form, all right? Or in other words, think about this, more reactants will react to form more products, right? And again, in the end, the equilibrium constant value will be constant, right? And that's how your AC train works, right? So if you think about this, you have this marble, right? The carbon dioxide is a gas. It starts diffusing out of this. It's a gas, it's going to go back to the atmosphere. So this is like removing carbon dioxide. So if you remove carbon dioxide, what's going to happen? The equilibrium lies towards the product side. More products are going to form, meaning that this calcium carbonate, which is our marble, is going to degrade over time, right? So this is the effect of removing a product from a LeChatelier's principle. Right, the next one we're going to look at is the effect of temperature. Now, temperature concept is slightly challenging, but then again, we're going to think about this in terms of adding reactant, adding product. All right. So now we're going to look at change in temperature and what will happen, right? So we're going to look at something called exothermic reaction. So we're looking at a reaction where hydrogen peroxide is at equilibrium, right? And then the products water liquid and oxygen gas is formed. Now this reaction is exothermic. How do I know it's exothermic? Because first thing, my delta H is a negative value. And next thing, other way to think about this as whenever you have heat written on the product side, I know that it's an exothermic reaction, right? So now if I add more heat, right, or if I increase the temperature, so again, if this is confusing you, think about this as we are in the middle box, right? So all I'm trying to do is now heat this middle box up. That's what I mean by adding heat, right? So remember, adding heat is the same as increasing the temperature. So if we increase the temperature, right? So remember, these are reaction. So I'm increasing the temperature means I'm increasing the heat, meaning that, so think about this as adding more product, meaning that more reactants are going to form, or it pushes the equilibrium to the left, or more reactants formed to establish equilibrium, right? Now, instead of heating the temperature, adding the temperature, right, or increase the temperature, if I decrease the temperature, so let's say this reaction is at equilibrium, I'm going to plunge this in cold water. So let's say this was at room temperature, I'm just going to plunge this box into cold water. So when that happens, in our case, right, when this removing heat happens, so think about this as removing the heat, which is on the product side. When you remove heat, right, the equilibrium will shift to the right, or more products are going to form when you decrease the temperature for this exothermic reaction. All right, now let's look at an endothermic reaction example. So this is an endothermic reaction, right? You have N2O4 going to 2NO2. All right, now how do I know this is an endothermic reaction? Because delta H is positive, all right, or my heat is added on the reactant side. So now we're going to look at two scenarios. What happens if I increase the temperature or add more heat, or when I decrease the temperature or remove this heat? So again, if I add more heat or increase the temperature, the endothermic reaction will drive to form more products, or the equilibrium reaction lies toward the product side. Whereas if I decrease the temperature, right, that means I am removing the heat. So think about that way. If I remove the heat, the equilibrium will lie towards the reactant side, or more reactants will form, and the equilibrium will be reestablished, but the equilibrium constant value will not change. All right. Again, there I could do more with pressure and stuff like that, but what I've done is to make your life easy. I have created this table for you, and it does talk about what happens when you increase the pressure or decrease the pressure. Right. So this, if you understand this table, you should be good. All right. So what I'm going to do is I'm going to just use this. All right. Now let's start with this. First thing, I look at this reaction. I see that it is added to my product side. That means this is telling me this is my exothermic reaction. Now let's look at the first stress that we just went over. If you increase the temperature, means you are increasing this or adding more product, right? If you add more product, the equilibrium will lie to the left. That's what it means. The direction of shift is going to be left, right? Or meaning that more reactants will form. What if I decrease the temperature? If I decrease the temperature, think about this as now. Let me see if I can change the color. This pen. So now this is decreasing the temperature. You're making the reaction colder. When that happens, that's the same as you are removing the heat. Whenever you are removing the heat, that's the same as removing the product, meaning that the equilibrium will shift to the product side. That's why you see the equilibrium will shift to the product side. All right. So I'm not going to go over this and this. Make sure you take your time to go over these. I'm going to go over the last two because we haven't gone over how does pressure affect the equilibrium. All right. So now, easy way to think about this is increasing pressure. So for example, like I said in class, right? If you have a reaction, right? I can either increase the pressure of the reaction, which I can do, for example, if I had a box that I can compress, right? I have increased the pressure, isn't it? Now, what happens is it says to decrease the moles of gas. So think about this as the direction of shift will happen in the direction where there is less number of moles, right? So if I look at this, I have 3 moles of H2, 1 mole of N2 on my reactant side, meaning that I have 4 moles in total. Hmm, I want to pin. All right. So I have 3 plus 1, 4 moles on my reactant side, only 2 moles on my product side. Now, if you look at, if I increase the pressure, it says the reason for shift is to decrease the number of moles of gas. Look at that. I want to go in the direction where there is less number of moles. So 4 moles on my reactant side, 2 moles. That means if I go to the right, or form more products, right, to establish equilibrium or reestablish equilibrium, right? Now, if I decrease the pressure, which I can do by expanding that box. All right. So if I do that, it's just gonna, the shift will happen in the direction where there is greater number of moles, meaning that 2 moles on the product side, 4 moles on the reactant side. That is why the equilibrium lies to the left, or in other word, more reactants will form. Right. Now, one thing that I do want to add, right, to this, which is not sure, I think we'll work to this problem and that should answer the question, right? So, for example, we're looking at this reaction directly taken from Denniston's textbook, and we're gonna predict the effect of different stresses, right? For example, what happens if you increase the concentration? What happens if you decrease the concentration? What happens if you increase the temperature? And then what happens if you add a catalyst? And we're going to see whether the equilibrium lies to the left, or meaning that more products are going to form, sorry, reactants are going to form, or lies to the right, meaning more products are going to form. And let's look at the first one. All right, so again, this is the reaction that we're interested in, right? You have calcium 2 plus reacting with hydrogen carbonate anion to form calcium carbonate, carbon dioxide, and water. Now, it is this reaction right here, right? If you're interested in caves and stuff like that, if you ever go to the caves, some of them, right? What you're going to see is you're going to see some kind of a rock formation from the ground going towards the ceiling. So those are your stalagmites. And then some of the rock formation that starts from the ceiling. So let's say this is my ceiling and goes pointing towards the ground. So these are like stalactites. All right. Now these form because of this reaction that's shown here. Right. As soon as I see this, I see that, oh, 4.67 kilocalories is on the reactant side. And this is how I know this is my endothermic reaction. And that will help me answer question number C. Let's start with number A. First thing is whenever the concentration of Ca2 plus is increased by adding some CaCl2. That means it's asking us what will happen if you increase the concentration of Ca2 plus. So whenever you increase the concentration of Ca2 plus to relieve that stress, right, the reaction will shift to the right, or meaning more products are formed to reestablish equilibrium. Let's look at the second one, B, which is the concentration of HCO3 minus is decreased. So now let me change the ink color to orange. All right, so whenever the concentration of HCO3 right here is decreased, right, the equilibrium will lie towards the left, right? Meaning more reactants formed. Because now the products are going to start reacting to produce more reactants, which is the same as saying the equilibrium lies to the left. All right, let's look at C, which says the temperature of the system is increased. Now, as soon as I see this, my heat is on my reactant side because this is an endothermic reaction, right? So that means if you increase the heat, that's the same as adding more reactant. If you add more reactant, equilibrium lies to the right, meaning that more products are going to form to reestablish that equilibrium since we increase the heat that's on the reactant side. And finally, adding a catalyst. All right, so if you add catalyst to a reaction, it doesn't do anything. The equilibrium does not change, right? It neither moves to the left, neither moves to the right. There is no effect in equilibrium if catalyst is added. If you recall from last week's lecture, what we said was the only thing that catalyst does is, this is my energy diagram. energy progress of reaction, right? So let's say this is my reaction. Energy of reactants right here, energy of products right here, all right? What we said was this right here, distance from the highest point of this graph to the energy of the reactant right here. Right here, the energy of the reactant, right? That's my activation energy. This right here value is my activation energy. If you add a catalyst, all that happens is the activation energy value gets lowered. That's all. Right here is the new activation energy. And that's what makes this reaction go faster, or the reaction rate increases. All right, this is all I have. And these are the concepts that you'll need up to this point for exam 3. So chapter 5, 6, and 7.